All right. All right. This is the conceptual approach to Gauss's law. I give you an understanding conceptually of the math that you're going to be reading about. Okay? So, conductor versus an insulator. All right, so what I have is I have a neutral conductor. And I'm going to put that neutral conductor in an external electric field. Okay? What happens in response to that? Simon.
It polarizes.
It does polarize. So this happens. You guys, did you see that subtle?
Yep.
Okay. That's about all it does. Okay. Remember when we looked at the percentage of electrons that constitute the charge and how infinitesimally small that was? Okay. Same idea. It takes, we'll say, nanoseconds to make that shift. Okay. So in this class, if you have, it'll shift until what point? Fun. Yep. See how this kind of makes a charged plate over here, and this has a positive charged plate over here because of that polarization. Becomes polarized. That sets up its own electric field, a secondary internal, due to polarization out of positive into negative. Which is in the opposite direction of this external electric field. This polarization continues until these two electric fields negate each other, cancel each other out. Because if it didn't, then the electrons would experience force and they'd still continue to move. Okay? They shift until the net electric field on the inside is equal to 0. Okay? That's what I need you to see is there are electric fields present, but the net electric field is equal to 0. Everybody all right with that? So, factoid, memorized, take it with you to the exam and thereafter. If you are with static electricity, a conductor will have a net electric field of 0 in the interior of the conductor. Always. Okay. If we're talking about circuits, no, that falls apart. But if we're in static electricity, the net electric field inside a conductor will equal 0. The net, there's multiple fields going on here, but combined effect is 0. That is like crazy important that you get that factoid in your brain. That is a really good data point. That is a good anchor. Like, I know this because the electric field inside is equal to 0. Okay? So, it polarizes. Okay, and that electric field is equal to 0. So the total charge is still 0. It's just been polarized. Just like water molecule is, net charge is 0, but it is a polar molecule. Okay. So net electric field is equal to 0. That's really important. So the mobile charges are on the surface are rearranged, so the net electric field is equal to 0. I think I'm just saying this lots of different times. Actually, it can be very complicated to achieve that, but we know at the end of the day that the net electric field inside the metal is equal to 0. As a consequence of 1 over r squared, distance dependent. Yes, again, real important. Okay, now that was a conductor. An insulator is a different story. Okay, when you apply a external field, what happens is the molecules polarize, not the entire object, but the molecules, because the electrons are trapped or held to the molecule. It's like, I've got my 8, stop messing with me. But it responds within the molecule. So the electron cloud is shifted over here rather than just kind of being centered. Does that make sense? Okay, so the molecules themselves polarize. And so the result of that polarization, so here's this orange stuff is from this charge. This is the electric field created by this, causing this to polarize. This effect weakens because the electric field is getting weaker as you go further away from this. Okay, that's just that is just a consequence of that equation. Okay, now, so the polarization effect weakens. Now, this sets up, these molecules set their own electric fields up out of positive into negative, which is in the opposite direction of the external field. But this polarized field is not strong enough to counteract this external field. So the net electric field is less than what the external field is, but there's still field going through it. It doesn't get canceled out. You all right with that? Okay. And when we get to dielectrics with capacitors, this is going to be an important fact. Okay. So it's roughly equal. It's this internal electric field is going to be much less than the applied, and that depends on the material, which we'll talk about when we get to capacitors. Good? Okay. So the location of excess charge. A non-conductor, an insulator, that's anywhere. It could be anywhere. It's kind of fabricated based upon the scenario. If you're charging by friction, it's where it was rubbed. In a problem, they'll say it's on the surface, or it's throughout the entire volume, or it's like they can make up anything for an insulator. It stays there. A conductor, however, the excess charge is always found on the inner or outer surface. Okay, not in the middle here. You good with that? Okay, so it's always on the surfaces. Okay. How it's distributed. Insulator again, it's however it started. Like it could be isolated, it could be just evenly distributed. It kind of depends on how the problem is made up. With a conductor, they always go to the surface. On a sphere, they spread out evenly over a sphere. But if it's a weird shape, then it has a tendency to congregate at points. We'll talk about why that is later. James.
How would you get a charge spot on an insulator?
Rub it by friction. Like when the black rod, that was an insulator, you got it charged. Beyond that, you're just kind of pretending. Like, let's make it uniformly charged. I'm like, well, that would take a process. Okay. All right. So, if you have a uniformly charged sphere where it's on the surface, this is okay. So on a conductor, that charge is going to go on the outside anyway. Okay. Remember, so like the hollow planet thing. Okay. On the inside, the electric field is equal to 0 in all of these cases. From the hollow planet idea. On the out, beyond that, out here, this behaves like a point charge where the charge would be here at the middle, that far away. Just like with the planet, we can say that this gravity behaves just like the masses are located at the center of mass. That's the distance between the centers. Okay. Good with that. So spheres that have stuff on the surface, like uniformly distributed, that's a happy place. That's easy. Okay. So, kind of giving it a chart here, and I posted this PowerPoint on Canvas. So, mobile charges, conductors, yes. Insulator, no. Polarization, entire sea of electrons moves versus an insulator. It polarizes, but the individual atoms or molecules polarize. Static equilibrium, the net electric field inside is equal to 0. Net electric field is not equal to 0 on the inside if there's an external field. Excess charge is only on the surface, and an insulator could be anywhere. The distribution is spread out on the entire surface, and it could be located anywhere. It could be located in patches. So that summarizes what we just went through. Josiah.
On the previous page, it says when r is less than the overall radius. So that's true for both conductors and insulators?
If it's uniformly charged only on the surface. Okay, you good with that? We will get to what happens if it's uniformly charged on the interior after we study Gauss's law. Okay. Thumbs up when you got an answer. Is everybody okay with D? Dangerous dinosaurs. A, B, and C are true. Good with that? Okay. Yeah, I'll let you read that. The difference between C and D is this is 0 and this is like undefined. Tell your neighbor. Correct answer is C. Inside is 0, outside it behaves like a point charge. All right, here's our playground. Ready? We have a neutral conductive shell, meaning there's a thickness there. It's a hollow sphere. Okay, and so it starts neutral. Somehow, some way, we like zap in, teleport some positively charged ball. I don't know. Call it proton. I don't know. Whatever you want to call it. Okay, positive. Just whoop. How. What we're gonna look at is how, like, what happens in response to that. Tell your neighbor. You guys did this last year, these slides?
He didn't call it Gauss's law. He just said, hey, look at this cool thing. So that's what it does. Hey, look at this. This is kind of neat.
Okay, well, all you with photographic memories, the answer to the question is why. Correct answer is? Correct answer is B. Okay, it does create an electric field, okay, that goes through space. Okay, good with that? As if it was the only thing there. That's not the whole story, but that is the electric field that that red thing produces. Okay, and it's going outward. So correct answer is B. Okay, so which way are the electrons in the conductive shell forced because of this electric field? Tell your neighbor. Correct answer is in the opposite direction of the electric field. You good with that? All right. So, how does the charge here? I don't have red. I don't have red. How's the charge here compare? Whoop, nope, just kidding. There's a charge in there. Just kidding. That's Q. This is Q. I'm just going to tell you this. We'll have a good conversation about this later. Correct answer is B, equal. Okay. So, what is the strength of the net electric field in the cavity, conductor, the single charge particle inside the conductor? Have a conversation. Okay. What do you say? Correct answer is A. Why? Because this is a hollow planet. The electric field created by these negatively charged things, and actually I should do this. With the electrons going that way, the protons are stranded. Does that make sense? Okay. This is a hollow planet. The electric field from this and this are zero on the interior of that. So the only electric field that's present inside this is from this guy. You all right with that? So, no, it can be thick.
So it doesn't matter that the negative charges are closer?
Yeah, because it's in the center. Like it's like in a hollow planet. Even if you have a thick hollow planet, right here, gravitational field is zero, or even there. Okay, I remember when we dug a well or something, and then we said, okay, at this point here, everything on the outside did not have effect of when we're that distance away. Cool with that? Okay. So, A is the right answer. Now, tell your neighbor.
What is it by a shift in electrons in the conductor?
The polarization. The fact that the electrons went into here, leaving behind the protons. So these electrons here that have shifted. Correct answer is C. Okay. The electric field is going this way. And guess what? Is everybody okay? These two fields cancel out. Okay? So that the net electric field in the conductor is equal to 0. Those are the two fields that cancel each other out. Okay? These protons, exposed protons, do not influence this because they're inside of a, like the net electric field from this outer rim here is 0 on the inside of that sphere. You okay with that? Okay, so that's why the net electric field is equal to 0, because the red field is counteracted, negated by the black field in here. Okay, and so really from this point on, these two fields cancel each other out. You right with that, Josiah?
And that would also be true if the one in the center was a negative particle, right?
Yep. Good with that? Okay. So, well, look at me. Just to make sure that's in there. Everybody go with C. Why? Because we just described it. Those two fields are canceling each other out. This charge behaves like a point charge as if it was located here, but it starts at this point going inward. Canceling this, these two cancel each other out. Okay? This would be the out, this would be the in. Thumbs up when you have a guess. Tell them why you think so.
I feel like it should.
Okay, correct answer is? Correct answer is not A. Correct answer is not C. It is B. How do you know? It's neutral. The conductive sphere is neutral. You're right with that? So whatever the charge on the inside, that has to be the charge on the outside to make it neutral. Good? Okay. Correct answer is B. Has to. We said this is equal to that. And we said that's equal to that. Therefore, that has to equal that. Good with that? Tell your neighbor. Okay, correct answer is? Correct answer is A. All right. This field, the red and the black have canceled each other out. True like forever. Except inside of here. This charge on the outside creates their own electric field that has the strength, same strength that the red would have had if it hadn't been canceled out by the black. How are we doing with that idea? Okay, it's a hollow planet as if the charge of this was located here. Good? Tell your neighbor. Tell them why.
If it's F, wouldn't the difference between us two is the net charge?
If they have to be equal conservation of charge, it's a neutral spread.
Wasn't it like something have this first before negative?
Oh,
I don't know if it was neutral beforehand or it was negative.
I didn't read that. Why is that in the picture?
Yeah. That's what I say.
Yeah, then it would be F. Nope, not F, D.
Yeah, okay.
Then it would be D.
Correct answer is okay. The inside needs to be a positive 50 to create a net electric field here of 0. But the whole thing has a charge of negative 150. So if there's plus 50 in here, there needs to be negative 200 on the outer surface to make the net charge negative 150. How are we doing with that idea? Okay. So this is at this location here. What's the magnitude of the electric field here? Tell your neighbor. Correct answer is has to be D. It's in a conductor. You just know it. You just know it. Okay? That's a fact. You can figure out why that happens afterwards, but you know that that's a fact. The reason why is this charge is equally distributed about the sphere, and that cancels that out. Okay? If it wasn't equal to 0, electrons would shift. It would be forced, and they would move until there would be 0. Okay with that? Thumbs up when you have a guess. Have a conversation and tell them why.
You're going to say it's a shallow water range, so I don't care.
Yeah.
A shaft is just a ring.
No, yeah.
Pick a ring, and then you leave stops everywhere that you spun it. Boom, you have a shaft.
Correct answer is?
A.
Correct answer is A. Okay. The stuff on the interior here is equally distributed. Sorry, on the interior and the exterior of that, evenly distributed hollow planet has a net electric field inside here of nothing. So the only thing producing electric field is from this charged sphere, but we take it as a point charge from here of charge capital Q. Okay. Correct answer is F. Why? It's in a conductor. Just lock that in. Okay? In a conductor. That is the only rationale you need. It's in a conductor in static equilibrium. In static electricity. Thumbs up when you have a guess. Tell your neighbor. Correct answer is dangerous dinosaurs. This becomes plus Q on the inside and on the outside to make this total -3. This needs to be a -4Q after polarization. And then that behaves like a point charge. Good? Okay. So that was a insulator. Sorry, that was a conductor. What happens when we do the same experiment with an insulator? Okay, so there is an electric field. We've established that. What happens because of what happens to the molecules? How do they polarize? Okay, is everybody, let's see, nice, I did draw that. Okay, so electrons go inward. The electric field on the inside of the molecules, which way is that going? Oh, add a positive and a negative. So add a positive into negative, add a positive into negative. Are we good with that? Okay. So B. Tell your neighbor. Because correct answer is A. Amazing orangutans. Does that start with an O? Sorry. Amazing apes. The red field is much stronger than the black field. Okay. Correct answer is, for the sake of time, outside is A. Because this electric field, the black, only exists in the interior. Okay, it doesn't mess with it on the outside. You all right with that? Okay. Oh, we'll call it good. Man, these are good questions. We'll pick this up on Monday. Remember, you got that reading quiz on Monday.